All right, well, it's time for us to do some practice using limits. So we're going to sort of test some of our intuition, our basic understanding, but also, of course, now we really get to start flexing our algebra skills and working with manipulating expressions. So, as always, make sure you try to do these problems as much as you can on your own before looking at the answers. The more that you can do by yourself, the better you're going to get. So make frequent use of that pause button. Only try to watch as much until you're stuck, and then say, okay, how do I get unstuck? And then pause again, right? And then you keep going. Because the more you do, the better you're going to be, and you're already great. All right, well, let's get into it. So, multiple choice problem. Given that the limit as x goes to 0 of f of x is 4, and the limit as x goes to 2 of f of x is 0, what can we conclude about the limit as x goes to 1 of f of x? Okay, so what do we say? Well, we have some points. We have 0, we have 2, and we're trying to figure out 1. Okay, so I know what happens over here at 0, and I know what happens over here at 2. So, over here I'm 4, and over there I'm 0. All right, well, they're not the same, so I go halfway in between, so maybe it's 2. Maybe. But that seems too tempting. They're trying to tempt us. I'm a little bit suspicious of this answer. Well, what are other options? Let's see. The limit converges, but we don't know what it converges to. Okay, well, that might be true. Okay. Let's see. The limit does not converge. Okay, well, that could be true. Maybe, maybe not. Or none of the above. So what's the answer? So what's our intuition? Our intuition says when we talk about limits, we're really talking about things which are nearby. So the fact that I know something about the limit as x goes to 0 says I know a little bit about what's happening near 0. And I want to emphasize the word near. Near means very, very near. And how near? Like really, really very near. So you might say, well, 1 isn't close, right? No. 1 is far, far off. Any fixed distance is far. So I know what's happening near 0. And I know what's happening near 2. But that's it. And the thing is that 1 is not near 0 and it's not near 2. So I can't know anything based on those limits, because the limits are only giving me information in a very local sense. So what does that mean? I can conclude. And the answer is, I can't conclude anything. And the truth is, anything could happen at 1. There's all sorts of behaviors that could happen. Well, so, since anything could happen, we can't make any conclusions. So the answer is none of the above. Okay, wow, that one's good. I like that. All right, next one. So, suppose we have that x squared plus 3x minus 10 over x minus 2 is our function, except when x is not 2. Now, it's a really reasonable thing to say that x is not 2. Why? Well, because when x equals 2, you're going to get a 0 downstairs, and that's bad. We don't like zeros downstairs. Well, what happens when x equals 2? Well, in that case, our function will be defined to be 1. Okay, so now we have our function, which is defined for all values of x. So, we have two questions. The first question, what is f of 2? Well, that's actually easy to decide, right? Because we can figure it out. We plug 2 in, and we say, well, where 2 is in the second row, so our function at 2 is 1. So f of 2 equals 1. All right, that's reasonable. Now the second question, what's the limit as x goes to 2 of f of x? So the limit as x goes to 2 of f of x. Now, how do we deal with this limit? One of the things to remember is that limits don't care about what's happening at 2. Why is that an important thing to say? Well, if we look at our definition, we say, hey, there's really two cases. One is the case of what's happening at 2, and one's the case of what's happening at not 2. So this not 2, that's what's going to be happening when we look at the limit as x goes to 2, because as we take a look at the limit as x goes to 2, we're not 2. Okay, so that says what happens is I can replace f of x by this expression. So we get that this is the limit as x goes to 2 of x squared plus 3x minus 10. Divide that by x minus 2. Now, one of the things you should get into the habit of doing when you're looking at a limit is asking the question of what happens when we plug in 2. We already can see downstairs we get 0. What about upstairs? Well, we'll get 4 plus 6 minus 10, which is also 0. And 0 over 0 means more work. More work. And this is good. We like doing more work. If it was too easy, where's the fun in that? Okay, so how do we do more work? Well, we see we have polynomials upstairs and downstairs. Because we got 0 when we plug 2 in, that means that 2 has to be a root of both the upstairs and the downstairs. All right, so that means that we could factor these polynomials. Now, the good news is it's pretty easy to factor the one downstairs. See, we're done. Ha-ha, that was quick. The upstairs could take us a little while. Well, actually not too bad because we know that 2 is a root. Since we plugged in 2, we got 0. That tells us x minus 2 is a factor of the upstairs. Okay. Now, how does the upstairs factor out? Well, let's see. We need to get to x squared. I already have an x, so I'll need another x. And we need to get to minus 10. Well, I already have a minus 2, so I need to have a plus 5. And it's good to check. X squared, good. 5x minus 2x, yep, 3x. Minus 10, all checks out. Life is good. Now, what comes next? And I know what you're going to say. We cancel the x minus 2's. Are we allowed to do it? And why are we allowed to do it? Okay, so first question. Are we allowed to cancel the x minus 2's? And I know what you're thinking. Of course we can. Why can't we cancel the x minus 2's? This is silly, Steve. Just let us do it. Okay, I'll let you do it. But why were we allowed to do it? Now, this is actually, there's a little bit of subtlety here, and I want to point out this is part of why limits are helpful. Why can't we cancel something? Well, the answer is we can't cancel zeros out. So anytime we have a potential division by 0, you can't just cancel it out. So how do we know x minus 2 is not 0? The answer is we're looking at a limit as x goes to 2. And when we take a limit as x goes to 2, one of the things we say is x is not 2. We don't care what happens to that 2. So we always have x is not 2, which means it's perfectly valid. This is always a non-zero number. That's always a non-zero number. We can cancel, and life is good. So, great. We can move forward. So now what do we have? Well, this is the limit as x goes to 2 of x plus 5. That's great. In fact, it's a polynomial. And so when it's polynomial, what do? Well, we just plug in our number. So 2 plus 5. Well, that's 7. Okay, so now we've answered both questions. So the limit as x goes to 2 of f of x is 7. Now, before we leave this problem, even though we're done, let's just note something. What does happen is 1. What should happen is 7. So here, this is a case where what does happen is not the same thing as what should happen. In some sense, what we have is that the function was not properly defined at x equals 2. It was poorly defined, maybe. Well, we'll talk about those kinds of functions another day. All right. Let's do a kind of a similar flavor. Suppose we have the following problem. G of x is the function which is sine 1 over x if x is not 0, and it's 0 if x does equal 0. Now the question is, what is f of 0, and what is the limit as x goes to 0 of g of x? Both good questions. Now, one of these is pretty straightforward, and one of them is going to make us stop and think for a minute. I think we both see this straightforward. The function, my goodness, there's a typo here. Shh, don't tell anybody. This is supposed to be a g. Okay, good. We're among friends. All right, so what is g of 0? The answer is 0. Good. Now, the real good question. What is the limit as x goes to 0 of g of x? Okay, now that one's we're gonna have to think about that. So, well, similar idea. Really, when we take a limit as x goes to 0 of g of x, because I know I'm not 0, I'm really into this part of the function. So that's the limit as x goes to 0 of sine of 1 over x. So, for us to make progress in answering this question, now we need to take a moment and think about, what does sine 1 over x look like? So, it's probably helpful to remember, what does sine look like? Well, the answer is the sine function looks something like this. It's called sinusoidal, which is a very fancy way of saying it looks like a sine function. Well, really it means that it's a wave, so it's going up and down. So this is the sine function. All right? So this is sine of x. And you can see that as I move along, I'm going to oscillate in a regular interval, and in fact, by the time I head off to infinity, I'll have oscillated up and down infinitely often. Now, what's happening? Well, we're sort of taking the inside and flipping it over. So, why is that interesting? Well, if you think about the function 1 over x, so let's sketch what that function looks like. It looks like this curve here. And if I were to come here to 1, what I see is that in this interval between 0 and 1, so in other words, when I'm looking at the values between 0 and 1, what happens is I capture all the outputs from 1 to infinity. So, what is that telling us? Well, what's happening here is that when I look at sine 1 over x, when I'm looking at x going from 0 to 1, the input is trying to cover everything that would normally happen from 1 to infinity. So in other words, if you come up to this curve here, all this part right here is what happens between 1 and infinity. And in other words, we're going to go up and down infinitely often from 1 to infinity. Now, we're going to take all of that information and whoosh, compress it. So, what's going to end up happening is that the sine of 1 over x, and this, by the way, is a very common example. It's going to slowly come up, and then it's going to come down, and then it's going to come up and down, and it's going to start oscillating, but quicker and quicker. And in particular, there's going to try to be infinitely many oscillations. So, in other words, as I move in towards 0, it oscillates infinitely often in that small amount of space. Now, what is that telling us? Well, the question is, what are we trying to understand? We're trying to understand what happens to this curve as I move into 0. And the answer is it's going up and down, up and down, up and down, up and down. What am I approaching? Well, am I approaching 0? Well, no, because there's many times when I'm kind of up near 1. So maybe I'm approaching 1. No. There's many times I'm down here, negative 1. Or maybe I'm approaching a half. No. In fact, what's happening is it's not trying to approach one value. It's almost trying to approach infinitely many. Everything between negative 1 and 1, it keeps going up and down and up and down. Well, you can't approach more than one thing. That's one of our basic rules of limits. And so because it's not making up its mind, what do we say? Well, that says that this limit is what we call DNE, which is shorthand for does not exist. So it's possible that our limits don't exist. Now, there's a variety of reasons why limits may not exist. This is just one of them. And this is a case where it's like, I can't make up my mind. I want to come up and down. The function sine 1 over x, we are going to see this probably several times in the future. It's a really great example because it sort of gets this idea of something that can move up and down a lot in a very short amount of time. So anticipate revisiting our friend sine 1 over x. All right. Now let's do another problem. Find the limit as t goes to a half of 2t squared plus 5t minus 3 over t plus 2 quantities squared minus t minus 3 quantities squared. Well, how do we do this? Well, the first thing you should do is you can say it's a rational function. Upstairs is a polynomial, downstairs is a polynomial. When you have a rational function, the reasonable thing to do is say, plug it in, and let's see what happens. So let's start by doing that. We're going to plug in a half. So currently, we have 2 times a half squared plus, 5 times a half minus 3. That's the top. Downstairs, we have 1 half plus 2 squared minus, then we have 1 half minus 3 squared. Okay, so 2 times a half squared. Well, that's going to be the same as 1 half. 5 times a half is 5 halves. And minus 3, which, by the way, since we're already thinking in halves, that's 6 halves. Downstairs, a half plus 2. Well, that's 5 halves squared minus a half minus 3. That would be negative 5 halves squared. And we see upstairs, a half plus 5 halves minus 6 halves is 0. Downstairs, 5 halves squared minus negative 5 halves squared is 0. So what does that tell us? Well, that tells us that we need to do more work. Okay, well, that's good. We need to do some work. We need to practice. So let's practice. Okay, how do we practice? Well, we want to rewrite our expression in some way to get some cancellation. So we have something causing a 0 upstairs. We have something causing a 0 downstairs. If we can figure out what are causing the zeros and get them to cancel out, then we don't have a 0 over 0 situation anymore. So that's our goal. Let's figure out a way to cancel stuff out. So, let's see. Now the upstairs we can factor. Now, we have an advantage. We know one of the roots. You see, t goes to a half. And by the way, t doesn't have to go to a whole number. A half is perfectly fine. So what does that tell us? Well, it tells us that t minus a half has to be one of our factors if we were to factor it out. Now, we don't have to use t minus a half. We could also use 2t minus 1. Just that could be another way to think about it. All right, so let's think about it. On the upstairs, what do we have? So we have the limit as t goes to 1 half. Well, we know one of our factors will look like 2t minus 1. So that's 2t minus 1. Now our other factor. Well, let's think about what we need. I have a 2t squared. I have a 2t. 2t times what gives me 2t squared? T does. Now, the minus 3. I have a minus 1. Minus 1 times what gives me minus 3? And the answer is plus 3. Now, let's just check our work. It's always good to check. It's a good habit to get into. So, 2t squared, yep. 6t minus t, yep, that's 5t, and minus 3. Good, good. Now, the downstairs. Now, the downstairs, you have 2 options, and they both work. So, what's the first option? So, I'll outline the first option for us. Option number 1 is you expand. In other words, you have a square, square it. So, expand, then factor. So it would become what? T squared plus 4t plus 4. Right, that's what we get when you square t plus 2. Subtract t squared minus 6t plus 9. And notice my use of parentheses. Oh, parentheses. Such great friends. They help save so many points. And now, what can happen? Well, if you take the minus sign and distribute it through, you get t squared plus 4t plus 4 minus t squared plus 6t minus 9. And now you say, ah, cool, the t squareds cancel. Nice. 4t plus 6t is 10t plus 4 minus 9 is negative 5. Or if I pull out a 5, I get 5 times 2t minus 1. Okay, nice. So I'll go ahead and put that in. Now I said there was another thing you could do. What's the other thing you can do? Well, one of the things you might get into the habit of looking for is there are certain things that show up a lot. And one of the things that will show up quite frequently, especially when we're doing our simplification, is differences of squares. So here I have a square minus a square. So I can use the fact that I know that a squared minus b squared is equal to a minus b times a plus b. So how do I do that? Well, what do we do? Well, so think of this part as our a, and here is our b. So a minus b. So that would become t plus 2 minus t minus 3, a plus b, t plus 2 plus t minus 3. Okay, a minus b, a plus b. So here, t plus 2 subtract t minus 3. The t's cancel. 2 minus minus 3 is 5. Here we get t and t, that's 2t. Plus 2 minus 3 is minus 1. 5 times 2t minus 1. Now, if you're like, wow, they were the same, you need to work on your algebra, because of course they're the same. It shouldn't matter how we simplify the expression. The way we go about simplifying the expression should not change the value. Rather, we'll always get the same. But it's nice to be able to know that we have options. Now, we're not done yet, okay? What have we done? We've set ourselves up to help us get a simpler expression. Oftentimes, most of what we do in math is saying, I have a complicated expression, I'm trying to get to an answer, let me do a sequence of moves that makes things simpler and simpler and simpler. And maybe, if I make things simple enough, it'll all work out. So here, we can cancel the 2t minus 1s. They're common. And similar to what we talked about in the last problem, we're allowed to cancel the 2t minus 1s because they're not going to be 0. So what do we get? We get the limit as t goes to 1/2 of t plus 3 over 5. And now we say, wait, this is a polynomial. Let's just plug in a half. So we get 1/2 plus 3 over 5. Now a half plus 3 is really 7 halves, right? Because this is 6 halves plus a half. And then divide that by 5. So if you clean it up, you get 7/10. And that's our answer. Now, before we leave this problem, I think it might be useful to just note a couple of things. First off, and really this is the main thing I want to point out, be careful with notation. Notice we kept writing the words limit over and over until we got to a point where we didn't have a limit anymore. This is important. You want to make sure you have good notation. Good notation can help you save points. And we want to get as many points as possible. So get into the habit of saying, look, if I haven't taken the limit yet, in other words, I haven't carried out the evaluation, I need to rewrite the limit so that I know what I'm doing. And if I have taken the limit, then I should not be writing limit again, because that's not a proper way to write things. Now, you might think this is just sort of me being annoying, but it's also helpful for you because it lets you better check your work. Remember, a lot of math is about communication. So you want to be able to communicate what you've done, not only to other people, but to yourself. You might be going back and checking your work, and if you look at it and be like, I have no idea what I was thinking when I wrote that. Huh? That's not a good sign. So you want to be coming in and saying, aha, I know what I meant because I can follow my argument. And so that's why you want to make sure good notation is very, very important. All right, good. All right, our next problem. Find the limit as y goes to 3 of the square root of y plus 1 minus 2 over the square root of y plus 6 minus 3. Oh, some square roots involved. Okay, spicing things up a little bit. We like that. Now, natural thing to do is first let's just check what happens as we plug in 3. So we say what would happen is we get the square root of 4 minus 2 upstairs. Downstairs we get the square root of 9 minus 3, which becomes 2 minus 2 over 3 minus 3, which is 0 over 0, which of course means more work. More work. Of course it does, because that's how we approach these problems, right? If they were too easy, it wouldn't be any fun. We like to challenge ourselves. All right, so what's our goal? We'd like to get some cancellation, but right now we have the square roots involved, and it's not so clear how we can get rid of any terms yet. There's no clear sense of cancellation. We want to get rid of our square roots, so we want to square them. Now, you can't just arbitrarily go around squaring things, because that's not how algebra works. You have to find a mechanism that introduces a square. So this is why we have conjugates. All right, so here we go. This is going to take a little bit of space here. So we're going to start here. The limit as y goes to 3 of the square root of y plus 1 minus 2 over the square root of y plus 6 minus 3. Now, I have a square root both upstairs and downstairs, which means there's going to be a lot of stuff happening. I got to somehow work with the upstairs to get rid of that square root, and I have to work with the downstairs to get rid of that square root. Let's start with the upstairs. So the way we get rid of the square root is we multiply by the conjugate. So what I want to do is I want to flip this sign, and so I'm going to multiply by the square root of y plus 1 plus 2. So notice that if we were to square that out, well, I shouldn't say square them out, but we were able to expand that out, the square root would go away. And the important thing is, because it's a minus b, a plus b, your cross terms, that ab and minus ab cancel out. So that's why we like to do the a plus b, a minus b. Now, I can't just multiply by the top. I have to do, whatever I do to the top, I have to do to the bottom. All right. Now, that'll fix the upstairs. It won't fix the downstairs. So we're going to also do something to fix the downstairs. Now here we'll do something similar, except it's going to be square root of y plus 6 plus 3. So again, I'm just flipping the sign in the middle. Square root of y plus 6 plus 3. All right, so that's what we're going to do. Now it sounds fun, and well, if we're careful, we'll get a nice answer. Things will work out. So on the upstairs, we're going to multiply those two pieces together. Now you might say, well, shouldn't you multiply 3 pieces together? Here's when it's important to remember, you only want to expand something if it's going to help you. If multiplying stuff out makes things worse, then don't do it. So I only want to multiply things together, which will actually help. Now, what about the downstairs? In the downstairs, we're going to leave this alone because this is not helping the downstairs, it's helping the upstairs. And instead, we're going to take this last piece and this first piece and multiply those together. So let's carry out the multiplication. We're still taking our limit. So this is our limit as y goes to 3. Upstairs, we have y plus 1 minus 4. A squared, gets rid of the square root, b squared, 2 squared. And then you have a square root of y plus 6 plus 3. And parentheses. Make sure you get those parentheses there. When we do these terms, you're going to get y plus 6 minus 9. So again, a squared minus b squared. And then the square root of y plus 1 plus 2. All right, so far so good. Now, let's think about this? Well, let's clean this up. Y plus 1 minus 4, what's another way to write that? Well, we can write that as y minus 3. And y plus 6 minus 9? Y minus 3. Now, we should have anticipated that there should be something that looks like y minus 3. The reason I say we should have anticipated that is we know we need to get some cancellation going on. And we want to get cancellation of something where 3 is causing the 0. So y minus 3, that could be what's causing our zeros. So the fact that we got y minus 3 means that we've done some good algebra. We've lived a good, clean algebra life, and we're being rewarded for it. And now we can cancel the y minus 3's. So, woohoo! Farewell, y minus 3's. Nice to know ya. Nice to know ya. So, this becomes our limit as y goes to 3 of square root y plus 6 plus 3 downstairs square root y plus 1 plus 2. Now, let's see what happens when we plug in 3. And the answer is if we plug in 3 and we get a number, that's it. That's the number. So, upstairs, we're going to have square root of 9 plus 3. Now, this is promising. As long as it's not 0, then really it means we're done. We're done. Downstairs, what do we get? Square root of 4 plus 2. Or, if you like, that's 3 plus 3 over 2 plus 2, which is 6 over 4, or really that's 3 over 2. 3 halves. And that's the answer. See, notice that when we started with 0 over 0, in this case we ended up with 3 halves. In other problems we ended up with different numbers. We didn't end up with 1. Now, will we end up with 1 sometimes? Yes. But 0 over 0 is not 1. It's not 1. That's why we have to say you do more work. And, of course, the more work you do, the easier it gets. We want things to be easy. All right. Ooh, something involving trig. Find the limit as theta goes to 0 of sine squared of theta over 1 minus cosine theta. Well, what happens when we plug in 0? Upstairs, you get sine of 0 squared. Well, that's 0. Downstairs, you get 1 minus cosine of 0, 1 minus 1, or 0 over 0. Now, we see 0 over 0. What do we think? Of course, we think this means more work. More work. Well, that's because there's more work to be done. All right. Well, so how do we do that more work? Well, we need to find a way to cancel off something that's causing zeros. So we're looking at this and saying, well, is there any obvious cancellation? And there doesn't seem to be one yet. But we see trig involved. Whenever you see trigonometry, you kind of have in the back of your head, it's like, you know, there's a lot of identities in trigonometry. Maybe there's an identity that can help us here. Now, the classic go-to identity that we will encounter with trig is sine squared plus cosine squared equals 1. We're going to see that over and over and over again. So I see there's a sine squared, so let's replace sine squared. So we can say, hey, our limit here, as theta goes to 0, of sine squared of theta over 1 minus cosine theta is really the same as our limit as theta goes to 0 of, now sine squared is 1 minus cosine squared, and then you have 1 minus cosine. All right. Now you might think, oh, I'll cancel the 1s, I'll cancel the minuses, I'll cancel a single cosine, and then I'll just end up with the cosine. No. That's not how it works. That's not how it works. Let's be careful. What can we do? Well, if I want to cancel, I need to really make something similar. So we think to ourselves, how can we make 1 minus cosine squared theta look like 1 minus cosine theta? And after we stare at this for a while, we might come up with the sort of nice observation. You know, 1 is 1 squared. Yeah, that's true. Is that helpful? Well, what that tells us is, hey, that's a square minus a square. So square minus a square says it factors. 1 minus cosine theta, 1 plus cosine theta over 1 minus cosine theta. And now we're like, oh, yeah, we can get cancellation. Lo and behold, the 1 minus cosine thetas cancel out. So what do we get? We get that this is really the limit as theta goes to 0 of 1 plus cosine theta. Now, what does that do? Well, that's 1 plus cosine of 0, which is 1 plus 1, which means our answer is 2. So that's our limit, 2. Good, good. Limits are fun. It takes a while to get used to them, but remember the basic core idea. If it's going to 0 over 0, more work. If it's not, you're basically done. But how do you do the more work? Think about how to rewrite your expression. How can I rewrite this expression in such a way that I can get some cancellation of zeros? All right, good. Keep doing some more practice.